Hi, in this video, I'll be going through a course on probability. In the previous video, we have already seen two different types of continuous random variable distributions. One is the uniform and the other is the normal. Before going on to what I want to talk about next, we'll just continue on this journey about continuous random variable so that we expose to you different type of distributions that occur. While this video won't cover everything, I'll just show you some of the more interesting and relevant ones that I use very often. And one of them is known as the exponential distribution. The exponential distribution is a random variable with a probability density function, so PDF, of lambda e to the power of minus lambda x, and x has to be larger or equals to 0, and everything else is fx will just be 0. And as a result, you can find the cumulative distribution for the exponential, which is the following over here, where you just integrate from 0 to a of the PDF, and you get the following result: 1 minus e to the power of minus lambda a. And so we can also compute the expected value, and all this is really to help you practice and understand and familiarize yourself with the techniques when dealing with continuous random variable. So let's go through it. For the expectation, you are just integrating from 0 to infinity, so all the values of x times the p of x. So the p of x is lambda e to the power minus lambda x, and then you can just integrate by parts, which you can check my video on in calculus to understand more, and you get the following over here. So you gotta keep, then you integrate this following function minus away the integrate times the differentiate of whatever you have kept, and you do the integration routinely, and it will result in the following 1 over lambda. Likewise, you can also show that the variance of this exponential random distribution is 1 over lambda squared. And so when we use exponential distribution is that it is usually used to denote the length of time. So exponential distribution occurs for amount of time for a specified event. For example, the amount of time before an earthquake occurs, before a new war starts, before a new telephone call, and these are in practice to have followed an exponential distribution because of it fulfills certain criteria that you can read in the textbook in section 4.7. And what's the utility of this is that the exponential distribution is the only distribution that has the memoryless property for continuous random variable. And what does this mean? It means that the probability of x being larger than s plus t, given that you already know x is larger than t, can be reduced to saying finding the probability that x is just larger than s. And we think about it as the length of time. For example, if x is the lifetime of an instrument, it says that if it survives for at least s plus t, and you already know that it survived for t hours, then it is basically the same as starting from t hours and whether or not what is the probability that it survives for the next s hours. So that's why you can remove the t portion over here. And so it is just saying that probability of x being larger than s plus t is the probability of x greater than t times the probability of x greater than s. And really, this memoryless property is very useful because it helps you simplify your calculations. While we will not prove it, it is actually possible to show that a continuous random variable with the memoryless property has to be exponentially distributed. And so you can take a look at the textbook to do more examples about exponential distribution, but I've hoped I've shown you what it is and now you can use it. For the next part of the video, we'll be talking now on how do we find a distribution for any given random variable. So for example, we already know x is uniformly distributed over 0 and 1. We want to know what is the distribution of y, which equals to x to the power n. Well, because x is within 0 to 1, y will also be staying within 0 to 1. And so what you need to do is, the standard method is to write the cumulative distribution. So you write p probability of y being less than or equals to little y. And now you can sub this capital Y as xn. And then you take the nth root, which will keep the sign since the nth root is monotonic function. And then you're already calculating what is the CDF of this at y to power of 1 over n. So that's probability of x being less than or equals to y to power 1 over n. And since x is uniformly distributed from 1 to 0, it's just the length from y to 1 over n, which you can solve easily. And as a result, now you know the CDF, you just need to differentiate it to get the PDF. And so you differentiate with respect to y, you bring down the power and then the power minus 1. And so it's really that simple in finding distribution. We'll take a look at more examples to familiarize ourselves with the method. And so let's say now that x is just a random distribution with a density of little fx. And then we know y equals to x squared. Similar to what we did before, what we need to do now is write the CDF of y. And then we sub in we replace y with x squared. Now when we square root, we need to take note of having the minus square root y side. And this is really saying it is the probability of x being less than or equals to square root y minus away the probability x is less than or equals to minus square root y. And this is just the CDF evaluated at square root y, and this is the CDF of x evaluated at minus square root y, which is the following over here. And so by differentiating, you're able to convert this CDF to its PDF I mean, and you just apply the chain rule accordingly. Example 7c illustrates now the case where we have a absolute value function instead of a squared function, but the idea is the same, and as a result you'll get the following conclusion. Throughout the course, it's more important that you understand the technique of finding distribution, so that you don't need to keep memorizing every type of distribution, and you can derive new distribution from old ones. In future videos, we'll talk about more general transformation, but for this single variable, random variable, we can just apply the following technique. So that's really all for this video. It's a short one for you to better familiarize yourself with more different distributions for continuous random variable, and I'll catch you in the next video. Thank you for listening and have a great day. Bye.